Hi, Dr. Hoda.
Hi everyone, how are you? Thank you so
Hi.
much and team for hosting all of us tonight with you and with your team. It's always a pleasure to collaborate with you and the team.
Yeah, we are delighted to have you with us tonight. Thank
Thank
you
you so
for
much.
making the time. And
Good morning, good afternoon, and good evening, wherever you are connecting from the world. I'm Hoda Alkhzaimi. I work in NYU Abu Dhabi as well as assistant professor in Department of Engineering, and I'm lucky to be surrounded by a very supportive research community in UAE with TI and NYU others as well. And today and tomorrow, you will be seeing a lot from my group, from the cryptographic group or the cryptographic team in NYU Abu Dhabi. So I hope that you will have a very informative and insightful session with all of us. So today I'm going to talk a little bit about the work we have been doing in hardware cryptography and the challenges and prospects that exist in that kind of framework. I don't know if you can see my slides. Are they changing? Yes. So the main design and motivation, the main motivation in here is to make sure that you are putting on the table a trustworthy cryptographic primitives that is efficient, both in terms of space, energy, and gate equivalence, and at the same time in terms of the attack parameters that is being covered and represented on the space. So it's secure to be handled within specific boundaries of complexity. And at this moment, I don't know how much our global audience knows about crypto, but within the field, when we are discussing, I would focus today more into block ciphers and ciphers cryptosystems. So we do have symmetric, asymmetric, then mixed models, the one that we have heard all day long today, which talks about the hybrid systems or authenticated encryption or quantum-based cryptography. And when it comes to today's world, hardware-based crypto is a must, and it's a challenge and in the wild, as we can say, and something that we keep looking forward to perfecting because it exists everywhere within the platforms and satellite avionics systems and RFID tags and energy harvesting devices, the wearables, you name it. And since the history of times, we have like a few standardized and non-standardized ciphers and cryptographic primitives that has been used within different platforms, as you can tell from my graph there. I'm sure the graph is cut a bit for some reason, but you could just get to see it on multiple levels. So within a crypto system, what you care about is that you do have an input and an output. You try to send it, and then there is a constant attempt of attack that exists on the system. And for that, we try to aspire to design within the hardware parameters something that is efficient, as I've said before. We do have different design aspects like substitution permutation network, our ARX designs that we will focus on tonight and talk a little bit about, and many different ones. So this is an example of substitution permutation networks, and I wanted to talk a little bit today about the invariance of space attack, but I think I will skip that since we had a session about it. It's a design that you can see in AS, for example, and many other ciphers and feastal structures and ARX. Are we secure and are we 100% within our own spaces? When we talk about, we talked about, sequencing the genomes a while ago, and we talked about security of the pacemakers. We still see attacks arising on there. And when it comes to cryptographic parameters, we still have this kind of constant struggle to push the boundaries of design and the boundaries as well of analysis. Because again, as we have heard today, once more, there is an impact of a quantum, or the impact of the quantum challenge that introduced a huge impact on all of us to work for a better security margins when it comes to key sizes or output lengths or complexity of attacks that are being conducted on so many levels. So the standard margins that existed in the classical old days, or I don't know if it's old days in some kind of a standard crypto, are like 128 bits. And in a while, I will just discuss as well the complexity boundaries so you could understand why we are going there. But for lightweight crypto, we're trying to push it for something that's lower than 128 without sacrificing the security parameters here in hardware in terms in order for us to just be able to fit into certain energy and power consumption requirements, gate equivalence requirements, and latency and throughput requirements, in addition to other software requirements. Few of them have been successfully standardized, and my list is not exhaustive. It's just a matter of an example here. We have Present, we have Prince, we have Cliffia, we have many others. We have authenticated ciphers, and also in post-quantum primitives. We've seen primitives like New Hope, for example, being used in Google platforms and many other platforms. So the key aspect is here is how can we build a trade-off between just building a tighter security margin and a tighter hardware margin as well. And the only thing that we have on the platform is the ability to just constantly analyze the design in order to provide a better assurance level of what we have on the table today in terms of security. And this is what we are striving to do all the time. So when we look at the landscape of how can we analyze these ciphers, for example, we are working for a global deduction or a total deduction, which is a dream for an attacker or for an analyst, or for a partial deduction through the statistical attacks of linear differential, and then you do have the side channel attacks. And today and tomorrow, you would see our aspiration in terms of trying to merge the boundaries between using statistical attacks and hardware attacks in order to achieve better complexity margins when it comes to improving attacks results on hardware spaces. The classical power of attacks we've seen before, 128. Why 128? Because it has been considered classically that 2 to 128 is very strong kind of combination that is hard to be analyzed for block ciphers, not very much for hash functions and others. And but with the current post-quantum and quantum efforts, this is not enough. So even for hardware primitives, we are facing a bit of pressure in terms of getting there or on the map. So let's see what we have done a little bit. This is a work that we have published in Africa Crypt, which is a joint work with my PhD student Sumesh Monjanat, and today we're going to discuss a bit how did we approach analyzing ARIX-based ciphers as a showcase study here. So we try to analyze the addition box structure within the SPARX construction, and we chose the smallest variant in there, which is the 64-128, using combined DBA techniques and first order and second order, of course, DBA techniques. And simulated an extraction of a full key recovery. The contribution here is to try to have a correlation power analysis and eventually try to just have a full attack on the cipher and introduce countermeasures and reapply the analysis again if possible on certain parameters. Then why did we choose SPARX specifically? Because again, it has been announced that it's a very good candidate, for example, to be used in IoT platforms. It has a very kind of appealing, I would say, a confusion network that we wanted to work with. So again, the results that we have anticipated were very promising. So SPARX is belongs to ARX family. It has three variants, 64, 128, 128, and 128, 256. The general structure, it works on steps like kind of a structure where you have n number of steps. Each one of them would consist of array rounds and one linear mixed layer. The confusion comes from the nonlinearity is achieved through the addition box, and the diffusion of bits is achieved using linear mixed layer, as we have just said before. These are the parameters that we are working with, the one in red in there. The first step for us was to just analyze the iteration function and the one round key schedule for the cipher. And upon analysis, I'll go through the results in a while. So why side channel attacks? What is side channel attacks? We try to work with different kind of measures until we decided on DPA. And again, in the portfolio, we do have timing analysis, for example, where attacker could exploit the timing difference in the execution of the cipher. The operation in the ARX design are almost constant, supposedly. And if there is a variation there in the timing operation, then this would give you synopsis on the key operations that exist within the platform, the key secret operations. And the power analysis, where the attacker could analyze the power consumption of a cipher to extract information on a secret key, and electromagnetic analysis, where attacker could exploit electromagnetic radiation emitted by the encryption devices, in addition to acoustic analysis and many others. So in terms of power analysis, we do have the simple power analysis, where only few elements of knowledge of the implementation of the cipher and the device are required. The power consumption is analyzed directly, so power traces must be bounded by a minimal noise, and the fact that few traces would be efficient to just utilize the attack. For differential power analysis, again, you would need knowledge of the cipher, which is sufficient, analyze the power consumption and dependency on the process data, and using the power model in order to achieve the analysis. The more power traces that are available, the better, of course, the attack results. In terms of correlation power analysis, this is a DPA-based attack. Using correlation technique like Pearson correlation efficient, which is a very efficient technique to resemble the actual power consumption and Hamming distance and Hamming weight model. And it would be easier for us as well to get accurate results on this. So initially, as in any other side channel kind of analysis, you would work on the operation that consumes the power during the execution, and you would use the oscilloscope to record the power consumption at a certain sampling rate. This would give you certain sampling points that you could work with in order to extract these power traces. The power consumptions is directly analytical to, for example, the transitions that would happen on the platform. And we have talked earlier, I think, in the day about the difference between Hamming distance and Hamming weights, and bringing different analysis variation. So what we used here is first the Hamming distance between the data before the input and after at the output, and the operation of our interest, for example, that you want to analyze in this source. So in order to build the Pearson correlation coefficient, you need to analyze the linear relations between the data sets. So it's more into understanding the linearization aspect. So if we have, for example, two data set, 1 and 2, the first one could be for the power traces of n plain text of encryption, and the second one would be for the Hamming distance between n plain text and encryption results that you are anticipating for the rounds. This is the general structure here, and you could see how it would work. for example, for our input and output of the data. And then we work for the first order correlation power analysis. For example, you would analyze different plaintext encryption power traces, and then you would try to build a hypothesis for each key using the Hamming distance values, and then calculate the PCC or the Pearson correlation constants, and then work with the highest value that you have within that hypothesis. Hypothetically, the key with the highest PCC value is going to give you the correct key guesses. The input can be easily masked using different masking techniques. Of course, this would protect you against this level of attack. If input is masked, then you have this kind of approach would fail. The second order correlation power analysis is the fact that when you have a secret key that can be masked using, for example, a random value to resist first order CPA, then the assumption here that a random value will be able to generate, a random value will be generated, and then a masking operation will be performed at a different point of time in order for you to be able to have a basis of comparison. If we assumed that at a certain time on instant, we could collect the power on the specific operation without masking, then you would be able to analyze and collect as much of traces as possible here. How can we perform this, for example, on addition modulo 2 to the power 16, which is the platform that we will be using on SPARX. CPA technique is applied to in this sense, or using the least significant bits until you get to the most significant bit on the input, because of course of the effectivity of using the carry bits. For us, we are highly interested in the addition, of course, because that's the operation that we would like to analyze. And initially, after extracting the least significant bit, we'll be able to completely get the secret key exposed, and building different hypotheses for the key would get you to the correct secret key ultimately. So this is a bit of simulation of what I've just been saying. So you could see here, this is a round of SPARX. And then you could see that using CPA, the 16 bits that would exist, for example, on the right side is extracted using 2 to the power 9 key guesses. For each 8 bits key, the Hamming distance is something that similar to the XOR values of the input, the XOR value of 2 inputs, the mask value in this sense. And then we will be able to collect these power traces and get the highest PCC in order for us to analyze what is exactly the key size that we are looking for in this analysis. I'm going to fast forward a bit. For example, if we apply this on a round function, on the whole round function, then we can get to see that the size of the key 0 here will be the concatenation of both the left sides for 32 bits of a key. Okay, so we have specific observations on the key scheduling that were used for the attack. We discovered that, for example, on the left side, there is a bit of parallelism between certain key bits that they are equivalent to each other. So the first bit from a specific precedent round is going to be constant in the next round. And the same thing as well for another round. And this is what helped us as well, configure the attack. Then we are using this on, for example, 4 rounds structure. We have been able to detect this pattern into 4 rounds, and using this 4 32-bit subkeys, we've been able to deduce the key at the at 1/2 of the structure. So we always start with a certain plain text and then a round key. At round 1, for example, if you've seen here the traceability of the attack, you can just follow it throughout the 4 rounds of the structure. So we end up having an attack here with a total complexity of 2 to the power 12 for the final key, and for the subkey 2 to the power 10. The final results that we could get out of this, the main setup that we had is we used Sakura VGA power board with a specific sampling, and we used it to just recover the key using 6,500 random plain text that is encrypting using 128 bits. Yes, so this is an example of the power traces that we captured into the analysis, and our capture through the first round. Then we try to improve the implementation through implementing a threshold implementation in order for the input to be split into different shares and evaluated as output of shares. So we can ultimately get the combined extracted result at the end. So what we needed to satisfy are 3 major properties well known for the threshold implementation normally, which is the correctness, which means the splitting and combining of these shares will result in the correct value ultimately, and non-completeness, which means each function is an independent of the share, and thus the attacker cannot get all the shares. And balance, the distribution of the input and output should be maintained, which also relate to something similar to a diffusion property as well that we could have here. So after that, we try to just build a serialized implementation of SPARX. And that's the goal, of course, using the threshold implementation. And afterwards, using that, we were able to build the splitting of the different registers, and then use it in different rotational cycles in order to just get the final combined results of the round using 80 clock cycles and 48 round function, 32 linear mixes. So the TI achieved correctness, non-completeness, and balance. And then what we tried to do is build that as a countermeasure. For example, we used 2 input-output right now. We try to analyze this countermeasure and see how this would work. Would the XOR be applied independently on each shares, and then apply the modular addition and check the nonlinear operation ultimately. And that's what we have done at the end to extract the final keys. These are the shares with the different carries, as you can tell. And these are implementation results, where you can note the difference between a serialized and threshold implementation kind of SPARX-based approach. So you could tell that, of course, the serialized one occupies less area in comparison to any other approach. That was the work, ultimately the introduction of the work that we have done in the past on one of the RX structures. At the moment, what we're doing, which is an ongoing work that that you will be exposed to tomorrow, hopefully, we're trying to just generalize a combined approach of attack where we use the side channel results that we've got with the previous statistical analysis results using differentials and linears to improve the attack boundaries that we have for ciphers like SPARX and other hardware ciphers as well that might exist within this space of hardware ciphers. Another aspect of work that my research group is working on is how can we construct physically unclonable functions that are efficient for cryptographic devices. Basically, we are working with different teams from Khalifa University into fabricating. This is joint work with Dr. Bakr's team, where we fabricated a memristor-based PUF and did the analysis on the different types of attack that we can push on the PUF. And tomorrow, my PhD student and colleague Hiba will be introducing this to the team. We also worked on how can we push further the current fabrication process, maybe change a bit the technology that we're using and using photonic-based PUF to build a better analysis for these cryptographic PUFs. This is an ongoing work with our colleagues in NYU Abu Dhabi in the photonics department, and we're hoping that this work will be published soon. So in conclusion, we're still striving to push the boundaries of the design and the cryptanalysis when it comes to hardware implementations. And we have demonstrated attacks on SPARX variants using 2 to 12 key guesses. And our future work would be combining these approaches together with hardware approaches, with the statistical approaches to further improve results, which is something not new, by the way. Plenty of people within the community have worked on this, but we're trying to just come up with novel approach and how can we reduce the complexity and ensure the efficiency of the attack within the given time complexity frame. Thank you so much for your attention, and that's it for me. If you have any questions, do let me know. Thank you so much. I hope for whoever is ending their day wherever you are in the world to have the best day ever. Whoever is starting your day to have a productive day ahead of you.
Yeah, thank you very much, Dr. Hoda. It was a very interesting talk.